Lecture 78, Falling into a Black Hole. So in this lecture we're going to try and describe, using spacetime diagrams, the Minkowski spacetime diagrams, what happens if you fall into a black hole. Okay? But before we get to that, we have to kind of set up a few things. So there's some weird things that happen when you accelerate particles, or when you accelerate things from relativity that you wouldn't expect. So for example, if I were to just imagine these points on a train, okay, maybe this is where the clocks are located, right? And the wheels, right? But instead of a train traveling at constant velocity, let's make this train accelerate with some constant acceleration a naught, right? So the first problem right off the bat is that after a sufficient amount of time, this train is going to be going faster than the speed of light, and that's not permitted, right? Yeah. So that's one of the things that happens. But the weirdest thing that happens, I guess, is if I were to remove these, well, the distance between particles, right? Say between the back of the train, if like put our observer back here on the back of the train, and say the front of the train, right? These distances change over time, and this is a fairly hard thing to understand why it is. For those of you watching at home, if you're interested, you can look into something called Bell's spaceship paradox, sometimes Bell's rocket paradox. This is related to this idea. It's a little bit different, but if we imagine that the acceleration, the uniform acceleration that we experience is due to a uniform gravitational field, for example, such that every point on here is being accelerated at the same rate, then what we find is that the distance between points increases over time. So if we tied sticks to each of these, or excuse me, if we tied strings to each of these clocks, the strings would stretch taut and then break as we continued in our acceleration. And it's a little bit weird, it's a little hard to think about. The origin of it, if you think about the relativity of simultaneity, you might remember that this kind of delta t sub s for simultaneity is equal to its gamma times v times the length, right? That's with the speed of light being equal to 1, right? So you can see that the farther away the point is that we're considering, right, the more out of sync the clocks will be, okay? Another way to think about it is that as we accelerate, there's a length contraction taking place, right, from an inertial reference frame. Now this is the part that's a little hard to wrap your head around, but you can think of it like, because of this decrease in length, the back of the train has to accelerate more than the front of the train in order to keep the points separated. Now we're talking about Bell's spaceship paradox. But again, it's kind of related, right? The fact that the accelerations at these different points, right? You can think of it like an impulsive acceleration. So I accelerate for a moment up to a certain speed and then stop, take a break, hit it again, kind of like Newton did with his orbits, right? Yeah. So what you'd find is that the person in the back of the train, right, would have to accelerate, I hope I'm getting this in the right direction, would have to accelerate slightly longer in order to match the velocity of the front of the train, okay? Okay. It's either that or the other way around. I don't remember which. But nonetheless, though, this weird phenomenon takes place where the distance between points, right, from the point of view of this observer, right, on the back of the train, would increase as time went on. So it's a little bit weird, right? Yeah. Now I planned on going into some detail with the talking about the proper time, and in the proper time you would find that this is not the case, but I decided that it wouldn't be worth it to go down that rabbit hole because it's a mess. So let's just take it for granted that this is something that happens. What I do want to do instead, though, is talk about uniform acceleration. So this is true uniform acceleration, something you can't actually achieve, but you can approximate it if you're, say, a very small body near a very large planet, right? Yeah. If your space station that you're on or whatever is small compared to the size of the planet, then it's approximately a uniform acceleration you're in. So if I put an accelerometer on the far side, on opposite ends of my space station, and they both register the same accelerations, or approximately, then we can say, well, we're in a uniform gravitational field or a uniform acceleration, okay? As we free fall around the planet. So what I want to do now is just draw on an analogy, okay, to the orbits we talked about before. Let's talk about circular orbits, right? And let's do it in like polar coordinates. Here we have a circle of radius r, let's say, right? And let's imagine this is our little orbiting planet. It's got some velocity v that's tangential, right, to that point. And it makes an angle theta, right, with the, call it the x and the y axes, right? Yes? I can decompose this guy's position into x and y using the following transformations, right? So the x-coordinate of this point, the rocket ship or the orbiting body, right, is going to be given by x will be equal to r times the cosine of theta, right?
Yeah.
And the y-coordinate of this guy will be given by y equals r times the sine of theta, okay? And since it's a circular metric, so to speak, we have the Pythagorean theorem, which says that r squared equals x squared plus y squared, yes?
Yeah.
If I want to describe the equations of motion in polar coordinates of an orbiting body in a circular orbit, right, it has a constant radius, r, right?
Yeah.
R is some constant, okay?
Okay.
And d theta dt would also be a constant number, right? The theta as a function of time, of course, is changing, right? It starts out at 0, goes to pi over 2, then to pi, and then to 3 pi over 2, and then to 2 pi, right? And then back again, and so on and so forth. But, yeah, it's very simply described in polar coordinates. Now, this won't work for, well, how do we say this? It turns out to be convenient to make an analogy to the circular polar coordinates that we just did here, but for general relativity. Well, for special relativity, excuse me. Let me say that more precisely. For special relativity, okay? And what you can do is, well, we'll use, remember that distances in Minkowski spacetime aren't given by this, right? The Pythagorean theorem doesn't work anymore. We get something that's kind of weird, right?
Yeah.
We're going to call this big X, and we're going to call this big T. You can think of it as time and position if you'd like, okay? And as it turns out, and we always want to draw in our light lines, right? When we're drawing a Minkowski diagram or space-time diagram, yes?
Yeah.
So the analogs to these polar coordinates are hyperbolic coordinates, okay?
Okay.
And what you end up getting is that X is going to be equal to, I'm going to continue to call it R, okay, times the cosh. That's the hyperbolic cosine, and I'll continue to call it theta, okay? It's not really an angle, though. It's a hyperbolic angle. It's kind of like an angle, but not really, okay? Y is R times sinh of theta. These are functions that can be used to describe hyperbolas, okay? So instead of this circle that you see here, instead we'll have a family of hyperbolas, okay? Remember, they asymptotically approach these light lines, right?
Yeah.
Additionally, we'll have the, oops, I want to write it the same way I wrote this. The r squared that we're talking about here is going to be equal to x squared minus t squared, okay? This is supposed to say t, by the way. I'm sorry, I messed that up. This is t. This is my t versus x-axis. We're talking about a space-time diagram now, right?
Yeah.
So this was just space, so x and y were spatial dimensions. This is space-time diagram. So we have one spatial coordinate and one temporal coordinate, right? And if we go back to our lesson on how to measure distances in special relativity, we'll find this formula here, right? It looks like the Pythagorean theorem, but a little bit different, okay? It's what makes measuring, trying to guess at what distances and stuff are in space-time diagrams difficult because of this, right?
Yeah.
So lines, points that you think are farther from the origin than other points turn out not to be when you use the correct measure of distance in space-time, okay?
Okay.
So if we do this, it turns out that we can think of, we can think of theta as a time-like coordinate, okay? Remember that when we talked about the invariants in special relativity, we talked about these hyperbola, and we noted that hyperbolas over here we call time-like, right? These are places that we can get to in time, right? Because this is our speed limit, right? So if we're not moving at all, we're just going up like this, right?
Yeah.
If we're moving with some velocity, then we'll make an angle to that t-axis, right? But we can never go beyond the angle of 1 if we let the speed of light be 1, right?
Yeah.
Because you can't travel the speed of light. And so we call these time-like because they're places that we can get to in time. And we call these space-like, right? Because you can never get to this point, right? If I'm here at the origin, right, I can't access this same point in space-time. An event that takes place at this point in space-time, I'm never going to be able to see, or be present at, I guess you'd say. Get to it, I guess, because I'd have to travel faster than the speed of light to get to that point, you see?
Yeah.
So if I, make sense?
Yeah.
Okay. So it turns out that this angle theta that we measure, and you can measure it like this. Let me see if I can use a different colored pen. I think this one's getting low, so let me use the green pen perhaps. Along the x-axis here, right, this would be theta equals 0, and we could get theta equals 1, theta equals 2, and on and on and on until we approach, basically the light line that you see here is theta equals infinity, okay? But theta is going to be equal to tau, that's the proper time, right, over r. That's the, and so what is r? R is like our space-like quantity, okay? So you can think of it as distances, okay? Rindler showed that these hyperbola describe uniform acceleration. So you could think of this as a body in free fall in a uniform gravitational field. This is the trajectory, right? So let's change this theta to t, just so we're thinking of time, okay? I lost my black pen. No, I had my black pen. I wanted my green pen. So this is t equals 0, we'll say, t equals 1, t equals 2, t equals infinity, okay? So this is a point at different times. So at t equals 0, right, we're at this distance r, right? It turns out that the r that it's from is this horizon here. It's the origin, but it's also this entire line, okay? That's the distance you are away from it. So if you're orbiting a planet at, say, a constant distance, you could think of it like that, I guess, but it's not really. It's this kind of, it's not a real point in space. It's kind of a made-up point in space, okay?
Okay.
But it's called the horizon, okay? And it's artificial. These values, t equals 0, t equals 1, they don't make any sense here at the origin. Only when you get farther away from the origin, out here, does it have any meaning to it, right?
Yeah.
But that's how we're going to think of it. We're going to think of it, well, in time, this is t equals 0. This is where the craft is located. And then at t equals 1, this is where the craft is located. At t equals 2, this is where the craft is located, etc. Okay? And then at t equals infinity, it's, remember, these hyperbola asymptotically approach these light lines, so it's getting closer and closer to that point out there somewhere. But all it means is that it's that distance r from this light line, I guess you'd think. It's called the horizon, okay?
All right.
So that's Rindler. And so what we're going to do is we're going to now talk about something slightly different, where instead of a uniform acceleration, right, that's special relativity under uniform acceleration, now we're going to talk about general relativity in a gravitational field, but with some caveats, right? So it needs to be using the Schwarzschild metric, okay? It's a particular solution to Einstein's field equations in general relativity. The kind of things that it can apply to are things like planets and stars, common everyday things, but they'll also apply to black holes, okay? And so that's what we're going to use, they're called Kruskal coordinates. I wanted to show you the uniform acceleration condition to give you some idea of how this is working, right? Okay? So this, what I've just drawn here, t equals 0, t equals 1, t equals 2, right? We're assuming this is going relatively slow, so proper time and coordinate time are the same, right?
Yeah.
Does that make sense to you?
So,
They really only start to differ when you're going really, really fast. Okay, if I was going 60% the speed of light, coordinate time and proper time are not the same at all. Remember, proper time is time measured at the same point, right? So you have to like be riding on the train, standing next to the clock, moving along with it in order to call that your proper time, you see?
yeah.
So, whereas a guy standing on the track seeing you race by, right, if he were to measure that clock time, it would be at two different positions, right? He'd measure first at this position and then at another position. The proper time is always measured at the same point, same position, okay?
All right.
But at these speeds we're talking about here, proper time and coordinate time are the same, okay? So, yeah, the distance from the horizon of this body, well, it's not even a body, this is just a uniform acceleration. It could be a rocket ship, okay?
All right.
And so this horizon is kind of a meaningless quantity, right? So this distance that we're away from it is completely meaningless, okay? So if we were to like try to do this and maybe approximate something like what's at the surface of the Earth, a gravitational field like that, would go way, way out, because these accelerations get very strong the closer you get in. And think of how much the hyperbola bends, right? A hyperbola like this, let's call this the r equals 1 hyperbola, right, is much bendier, right, than this hyperbola here. So we could call this the r equals 1, we could call this the r equals 2, okay?
All right.
So as r gets bigger, these hyperbolas get pushed back and out, right? So for Earth's gravity, maybe we choose r equals 100,000 or something like that in order to get the numbers to match up to the relatively weak acceleration that we feel here at the surface of the Earth, okay?
Okay.
Yeah, so now black holes. Well, usually people don't actually draw the axes for these. They just simply draw the light lines like this, okay? So it's understood that you've got a spatial axis going out this way and a temporal axis going this way, okay? But let's look at these different regions here. Right? So this and this are the only two physically meaningful regions. Okay? These regions over here really don't mean anything. Okay? The only time they ever mean anything is if you want to start talking about an Einstein-Rosen bridge, right? But we're not going to talk about that. This region here, let's start with this region here, right? Well, no, that's not it. Out here, we will have these hyperbola, much like what we just talked about. Okay? And these could correspond to, this would have a higher acceleration, uniform acceleration, than say this one would. Okay? And the closer in you get, the higher the acceleration gets. Okay?
Okay.
It's a little bit like having, closer and closer orbits, right? We're orbiting around a black hole. Now, I'm kind of abusing, you want to think that r equals 0 is here, but usually we redefine our spatial metric such that r equals 0 is somewhere else. A weird thing, these lines are not the angles they should be, but a weird thing happens here, and this is technically the r equals 0 usually, okay? This is the center of the black hole. So a strange thing happens with the coordinates, which is not real, it's just a kind of an artifact of the coordinate system, transformation. But spatial coordinates, if I were going to consider a bunch of orbits closer and closer, right, to a gravitating body, right? So smaller and smaller orbits, I draw circles, smaller and smaller circles, right? And so when you do that here, what happens is you draw hyperbolas that get closer and closer. And when you get as close as you can, at some point you flip, right, and you start drawing them over here, okay? And so it's this strange thing that things that were time-like become space-like, and things that are space-like become time-like, but it's an artifact, it's not real, okay? So when you're inside a black hole, your clock is not telling you how far you are from the event horizon or anything ridiculous like that. Everything is just as normal, okay? Also, I was going to mention, this only really applies to black holes that are very big, okay, such that near the event horizon, the tidal forces are negligible, just like they are, if you're orbiting our planet, right? You don't feel, there's not a big difference between the pull you feel at your toes and the pull you feel at your head, or the acceleration that you feel on your left arm versus your right arm, okay? So there are no tidal forces that are significant for this black hole. So it's a relatively large black hole, okay? Large meaning the radius is large compared to your size. So this r equals 0 that I've labeled here, right? This is the singularity, right? It is a true singularity, okay? So this is really the only orbit you've got in there, right? And what it's saying is that once you've crossed this line, it is inevitable that you land here, okay? Now there, the tidal forces would be extreme, and you would be ripped to pieces, of course, right? So that is a true singularity. The horizon, these light lines that I've drawn, which used to be in a Rindler coordinate system, just an artifact, just a construction, right, that doesn't mean anything. Here, this is the event horizon of the black hole. This is the place where light cannot escape from. I'm going to draw over here kind of a physical space. We'll call this black hole, okay? With a line that I've drawn around the black hole is what we're calling the event horizon. That's the point of no return, so to speak, okay? Yeah, and so here's the situation we're in. We're going to have a space station which is orbiting around the black hole at a pretty good distance. It is in an orbit that we'll say it's in free fall, right? So it's falling around the black hole. So we have a space station, that's our kind of inertial observer, okay? Now we also have a person that's going to fall into the black hole, right? Typically, the people that fall into the black hole are called Alice and Bob and Charlie and Dan, right? You see letters of the alphabet, A, B, C, D, right? So we'll call this Alice, okay? So let's see if we can use our, little bit of knowledge about space-time diagrams to figure out what it would look like from Alice's perspective, okay, as she fell into the black hole. Right? Her immediate environment is pretty simple. The event horizon is not even noticeable. She wouldn't even know she was crossing it, okay? Nothing is unusual about it. Nothing weird happens. You're just falling. That's it, okay? Now, of course, once you get close to the singularity, you're going to get ripped to pieces, right? Spaghettification, remember that? You'll be pulled apart this way and squashed together that way, and it's going to be terrible, okay? So, yeah, so certain inevitable death lies at the singularity, okay? But now we want to think about, well, what would she see as she fell in, and what would the space station see as she fell in? And so we can kind of diagram this. So here's how we're going to do it. So we'll draw, hopefully a little better this time. That's closer to 45 degrees. Call, it's not a good hyperbola. We'll call this the orbit of the space station, right? This is the hyperbola that the space station is on, right? And then here's the singularity. Again, not very good. Here's the singularity, right? And let's say that this is Alice. This is at t equals 0, right?
Yeah.
As we make these lines go closer and closer to the white line, that becomes t equals infinity, right? All right, so here's Alice, right? And this is her trajectory as she falls into the black hole. See? There we go. Right?
Yeah.
So what does she see at these different points, right? Well, let's think about what the spaceship, or the space station sees to start, okay? Because that's a little bit bizarre, and it's not what you'd expect, okay? Well, maybe we start with the case that you would expect. It's not all that unusual. Let's think about what Alice sees as she falls in. So how does Alice see stuff? Well, the spaceship has to send a signal to her saying, here I am, right? Maybe it's a ping, maybe it's just the light, reflecting from some, nearby light source, arriving at her eyeballs, right? But nonetheless, it's a light wave. And so we need to draw a light signal. I'll draw the signals in a different color. I think that would be good. So light in these diagrams is always this 45-degree line, right?
Yeah.
This, for example, is light traveling to the left, and this is light traveling to the right, right? So space station, light travels at this angle, right? Oh, yeah, wanted a nice line. There we go. This nice line right there, yes?
Yeah.
So here's the space station at this point. Light from it arrives at Alice when she's there, you see?
Yeah.
And we can continue to track her. What about when she's at the horizon, right? When she's at the horizon, now we need another 45-degree line. Try to draw it right. Something like that. She sees the space station right here at t equals 1 or something, right?
Yeah.
Let's call that t equals 1, right? She falls into the black hole. What does she see right before she's crushed and torn to pieces? Well, we just simply draw another signal coming from the spaceship. There's no problem, right? Remember, light can go in, it just can't come out, right? And so she sees the spaceship at this point, some later time, t equals 9, whatever. Okay?
All right.
So everything is normal for her as she falls into the black hole, apart from getting ripped to pieces, right? Spaghettified. Make sense?
Yeah.
Okay? Well now, and see how we did it though, right? Signals being sent from the spaceship travel at the speed of light and arrive at Alice. That's all you have to do is draw a line, right? So if you're interested in tracking Alice, just start from Alice and draw a 45-degree line backwards, right? Yes? So that's a light signal going to the left, right, to Alice, traveling at the speed of light, right?
Yeah.
Okay. So, see if I can erase this stuff without totally erasing everything. Because now I want to see what does it look like to the spaceship. Okay? What does the spaceship see? That's a little bit different, right? So that means that Alice has to send a signal to the spaceship, okay? So at this point, she'll send a light signal out. It needs to be parallel to this light line, right? So I'll draw a little ray like this, okay? So at this point in time, whatever that happens to be, that's when the space station sees Alice at this point here, okay? As she approaches the horizon, though, look what happens. So now we'll put her here. Draw another line like that. What's happening here, huh? Let's draw right when she's there at the horizon, just before she gets to it, right? We've got another line which is just barely diverging from the light line, yes?
Yeah.
We don't have enough room on the whiteboard to show where that's going to intersect this hyperbola, right?
Yeah.
So what time does that correspond to? Well, when she's actually at the horizon, any light signal she sends out is just going to be right on top of this light line we've drawn, the horizon line, right?
Yeah.
which means that the time at which the space station receives that signal from her is infinity. So from the perspective of the space station, what they see, right, is her forever falling into the black hole. She never arrives. Okay? So put it another way. Let's imagine that these things that they're seeing is her sending out a little light signal. At first, they're flashing at a regular pace, like maybe it's 1 hertz, so 1 flash per second, right? But as she gets closer to the horizon, right, as she gets closer to the horizon, the time between the pulses that she sends out, these little pulses of light, gets larger and larger. So there's less time, there's more time in between each pulse. So it's, flash, 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 flash. And it always gets longer and longer and longer between. And so eventually you're waiting forever for the next flash, you see?
Yeah.
So it's kind of weird. This is the gravitational time dilation stuff going on here, okay? From your perspective, that's what you're seeing, right? Her clock is moving slower and slower and slower and slower, okay?
Yeah.
So let's look at one more situation. I want to look at 2 people falling at the same time because something weird happens, okay? Any question you want to ask about what happens, though, you can draw it here, and it's relatively simple to, figure out, okay? So let's look at let's forget about the space station now, and I want to have 2 people fall in. We'll call them Alice and Bob, and they're both going to go in, okay? There's my light line. Put Alice back here again, but Bob is going to be behind her a bit, okay? So she goes first, and then he goes, okay? So his trajectory is going to look very similar, right? It's going to kind of... There we go, finally in there. Don't ascribe any meaning to the shape of these curves that I've drawn. You could draw a straight line if you wanted to, it'd be fine. So I'll draw Alice in green, and I'll do Bob's light signals in orange so we can kind of see it all together, right? So if we want to see what Alice sees, well, she sees Bob, right? Here's Bob's light line signal. She sees Bob here. I'll do the same thing again. She sees Bob getting close to the horizon now. It doesn't have to be, it kind of, maybe we'll even do it like this. Oops. Something like that, right?
Yeah.
So from her perspective, it looks like she went into the black hole first, right? Not surprising, right? She did leave first, right? What does Bob see? Well, here Alice sends out a signal to Bob. He gets it, say, here. Sends out another signal to Bob. When she's at the horizon, she sends out a signal to Bob, right? Signal to Bob. Signal to Bob. And finally, look at that. Signal to Bob. She sees Bob going first. Isn't that weird?
Yes.
She went in first, but Bob did not see her go in, right, until he was at the event horizon. Okay?
Okay.
So I'm not sure if this is accurate because I've never been inside of a black hole, but I think the idea is that once you cross the horizon, everything that's ever crossed it, in your eyes, now appears to be crossing it. Okay?
All right.
It doesn't mean that you're all moving at the same rate or anything like that, but you see everything come through. And so I think this is maybe the idea behind this thing they call the holographic principle, in that all the information about the black hole is spread out on the 2-dimensional surface of it, of the event horizon. Right? The event horizon in a real black hole would be a sphere, okay, not a line as we've drawn here. Yeah, and so all that information is contained on the surface of that sphere, right? So you take 3-dimensional information, you put it on the surface of the sphere. But I'm not positive. I don't know much about this holographic principle business. But does this make sense to you? Can you make sense? You just follow the light lines through. You've got to draw a light signal coming from the person that you want to see, arriving at your eyes, right? It has to obey the laws of physics and travel at the speed of light. If they're to your right, then you need to have a light line going to the left. If they're to your right, then you need a light line going to the right, you see?
Yeah.
Okay?
Okay.
So kind of weird behavior. And I hope I didn't mess it up. You can easily mess these things up when trying to talk about them, but give them backwards and whatnot. But that's basically it. That's what happens when you fall into a black hole. Questions?
Not really.
Okay. Yeah, I mean, again, any question you have, draw a picture, diagram it out. You'll be able to answer the question if you just think about it, okay? If you want to, What if I'm really close to the horizon and I stick my arm in and, you know, I pull it back out and things like that. So draw the diagram. It'll answer it for you, okay?
Okay.
And again, time, these weird angle kind of coordinates here. Yeah, and the hyperbola over here represent uniform acceleration, presumably from the gravitating body.
All right.
Okay, that's it. Next time we'll move on to something different. We're not going to do any more relativity or general relativity. Well, we will maybe talk a little more about general relativity and special relativity when we broach subject matter that needs to have that applied to it. For example, waves. We haven't talked about waves yet. That may be what we do next. Haven't decided yet. But once we talk about waves, we'll talk about Doppler shift, and we'll talk about relativistic Doppler shift. That'll allow us to then talk about gravitational time dilation, okay?
Okay.
All right, that's it.